will go over section 1.6, which is the concept of continuity. So continuity is the concept that your graph exists without breaks or jumps or gaps. So that means if your function is has solutions for all of the defined range, then it is continuous. Another way to think about it is if you were to follow the graph with your pencil or a pen, you wouldn't find the need to lift your pencil up. If you do lift your pencil up, that would mean your graph is discontinuous. So if I start with the concept A, if I try to follow it with my pencil over here, I can follow it all the way without I never lifted my pen. But if I look at the condition C, I can start over here, I lifted my pencil and continued over here. So that indicates it's actually discontinuous, and it does have a jump over here, so that's also another thing. So we're gonna go over these four main cases where you can see that it is continuous or discontinuous. For case A, we already showed that I never lifted my pencil. It has a solution for the range, so it continues for all values of the domain. For B, I see that it has a hole in the middle. So this means it's actually doesn't have a solution for x equals 1. It's empty. So it is discontinuous at x equals 1 only, because I see that it is actually continuous for the other values of the domain. So we also call this point of discontinuity because it is only discontinuous for one point only. For case C, it is discontinuous at x equals 1, but it is considered a jump discontinuity. So if you see it over here, x equals 1 is over here, and I see that it jumps from 4 to around 5.5, and it is actually continuous for and known for other values of the domain. For case D, it is again discontinuous at x equals 1, but it is considered the infinite discontinuity because it discontinues for an infinite amount. Not only at a point, it doesn't only have a jump, it is infinitely discontinuous at x equals 1. So there are two main conditions we need to satisfy in order to consider a graph continuous. So the first one, it's basically saying the function of fx is continuous at x equals a, which is a is any number, if fa is defined, so this is our first condition, and if limit as x approaches to a, fx equals to fa, which is our second main condition. First main condition is basically saying that at any number within the range needs to be defined. So previously, for the cases that we did, for case B, C, and D, we found that x equals 1 was not defined. So those actually don't satisfy the this condition for continuity, therefore discontinuous. For the second one, it's basically saying for at a point as x equals a, the function makes no jumps there, and that which means that x is close to a, that fx must be close to fa. So which makes sense for, if you think of case C, it had a jump. So if you put it into limits that x approaches the 1, it wouldn't give you a number that is close to 1, therefore it wouldn't be equaling to fa. So those are the two main conditions that they want us to consider when dealing with them. So otherwise, if these conditions are not satisfied, anything after that is discontinuous at x equals a. So a continuity problem that they might give you is like this one, where they give you a piecewise function and ask you to graph it for the a part. So I'm just gonna explain like how they graph the graph, but I'm not gonna actually do it. So here is your -1, and what they did is use the first function, and it says including -1 and less than -1, and that is x squared minus 3. You can already see that it passes through, normally it passes through -3 and comes up like this, and it's a parabola. Don't forget it's a parabola because it's x squared. So normally it's drawn like this, but it's not including anything after -1, so we wouldn't actually graph these parts. After that, what they did is they drew the second part, which is x minus 1. Normally x minus 1 would continue like this, but we cannot graph anything less than -1. So including like -1, we cannot graph it. So they would erase this part and got the whole function like that. So the second part asks us to determine limit as x approaches -1 fx. So what we're going to use is one-sided limit. So I see that for the left side, coming from the left side is represented by this function. So I'm going to do that. And coming from the right side for the second one is actually represented by this function coming from the right side. So when I solve these by plugging in -1 for each, so this would come to -1 squared -3. -1 squared would just be +1. +1 minus 3 would be -2. For this one, I'm going to plug in -1 again. So -1, -1 would equal to -2. I see that in fact they do equal to each other, therefore it's on a limit that doesn't exist. And then we can see that it is actually continuous. For part C, it's already something we found. So it's just saying if you plug in -1 for the x value, what will be your y value, therefore like f -1. So which is something we found here already. So C part would just be -2. So for part D, what we found is f continuous at x equals -1? I look at the graph, no jumps, no gap, no infinity discontinuous, like infinitely discontinuous. So therefore I can just say yes, it is continuous. And as an explanation, you can just say for the graph there is no jumps, no gaps, no infinitely discontinuous line, or you can say when algebraically solved, we found that limit in fact exists and equals to -2. So you can just write both just in case. So for this problem, it wants us to test the continuity of each of the following functions at x equals 2, and if it's not continuous, we need to give a reason. So for function A, I have x cubed minus x. Something I want to like clarify, for whenever you have a polynomial function, at all real values of x, they are going to be continuous. So either automatically you can say it's continuous, or you can actually plug in 2. So which I do that, I would get 8 minus 2 over here if you actually plug in 2. So 2 cubed minus 2 would be 8 minus 2, which would equal to 6. And if you actually solve for one-sided limits, you would actually be getting 6. So therefore this is in fact continuous. For the second one, I see that the function is not continuous, because if you actually plug in 2 for x's, I'm gonna get my numerator 0, therefore undefined. So anything that is not defined will just give me a function with discontinuity. This is the same thing that we did for part B, but instead now they give us a condition saying if x does not equal 2, but h, when plugged in 2 into the h function, I would get the value of 3. So in these cases, we actually need to solve it. So when I do that, I would get, let's say, limit as x approaches to 2, because that's what we're trying to find from like the main question. And then I have x squared minus x minus 2 over x minus 2. We're going to do what we did in 1.5. we're gonna simplify the numerator so that we can actually cancel out the denominator x minus 2 to get rid of that undefined stage. So here I'm gonna simplify it into x minus 2 and x plus 1, and then I have x minus 2 over here. I see that I can actually cancel these out, so I am left with limit as x approaches to 2 x plus 1, and that would just equal to 3. And I found that 3 actually equals h2. So therefore you can say hx is continuous really at 2. If you see a piecewise function like this, all you need to do is plug in 2 for the left side and the right side. I can see that this is the left side, this is the right side. For the left side, if I actually plug in 2, I would get 4 minus 4, which is 0. And I can automatically say, no, this is not continuous at x equals 2. So just a summary on continuity and on conditions. So a function f is continuous at xa if, like I said, fa is defined. So let's say x equals 1, they want us to find. It has to be defined for us to say yes, it is continuous. Limit as x approaching to a, fx needs to exist, which makes sense when we solved for one-sided limits. One of them didn't exist, it's just not continuous. For limit as x approaches to a, fx needs to be equal to fa, which means it needs to be actually approaching to that value, which we explained previously. A function that is not continuous has some type of break in its graph. This break is a result of a whole jump or vertical asymptote, which we explained in the first 4 cases. All polynomial functions are continuous for all real numbers. So don't forget that when we solve the section A for one of the questions. A rational function hx equals fx over gx is continuous at x equals a if ga does not equal 0. So ga meaning one of the questions was where the denominator is x minus 2 and x equals 2. So when you plug in 2, as soon as the denominator is not defined, it is discontinuous. So therefore our gx has to be defined, which we did in the questions. A rational function in simplified form has a discontinuity at the zeros of the denominator, which we did before. When one-sided limits are not equal to each other, then the limit at this point does not exist and the function is not continuous at this point, which the last question we actually approved. For this question, it wants us to find the values of x at which each function is discontinuous. So in this problem, it's a little bit different because it's just saying apply what you know as the conditions to find out at which values this time that x can be discontinuous. So for this, for E, I can think of, okay, it's in this form where I can say as soon as the denominator is not defined, it's discontinuous. So you can just equal it to 0, where it's like x squared plus x minus 6 equals to 0. If I simplify it, I'm going to get x plus 3 and x minus 2. And whenever the x equals to negative 3 and whenever the x equals positive 2, my function is going to be discontinuous. So those would be my values for E. For F, I can see that for the piecewise function that for whatever I'm approaching is the value 3. So you can think of this as limit as x approaches to 3. And then I have the left and right side in the piecewise function. So if I plug in 3 and not get the same things, then the function is discontinuous basically. I say for the left side, so negative x, I would be getting negative 3. For the right side, I would be getting 1 minus x as my function, which would equal to, if I plug in 3, negative 2. And I see that these don't equal to each other, therefore it's discontinuous. So you can say at x equals 3, the function is discontinuous. The question is asking us to find constants a and b such that the function is given by the piecewise function is continuous for the range of -3 to 0. So for this one, I want you guys to think about the one-sided limits that we did. So whenever you see a piecewise function, we do one-sided limits anyways, but when it says continuous, for it to be satisfied that condition, we said each left and right side has to equal to each other. So when we think of this piecewise function given in a graph, here is my -3, here would be my -2, and then my 0 is over here. Whatever is x's, it's between -3 and -2. So over here would be my, I'm not going to draw it, but I'm just going to say here is my -x, and then -2 to 0, and not including those. So I'm just going to say -x include these two, and then I'm going to represent the ax squared plus b by green, which is right over here, and not including 0, and then 0 is represented by 6. So right over here is actually, let's say this is 6, and here is my solution. So when solving left and right limits, I can say, well, for -2 portion, I can say x approaching -2 coming from left and right side, and see if they equal to each other, and have a one function from there. And then I can say my second function would be when approaching to 0, and have another function from there. And once we have two functions in the form of a and b, I can actually solve it to find what a value is and what b value is. So that's what I'm going to do. So for approaching to -2, I divided into left and right side. So for here, my solution would be plugging in -2 into my x. So -2 would give me +2. And over here, when I plug in -2 into my x, it's going to be -2 squared, which is 4. So I will end up with actually 4a plus b. And what happens is, if I want them to be continuous, I need to equal them to each other, because I don't know what a is, what b is yet. So my first function is actually, I'm going to put it right over here, is 4a plus b equals to 2. So for the second one, I said the left side would be ax squared plus b, because for it to be approaching to 0, it comes from here. Therefore, when you plug in 0 for x, you would end up with b. And the second one, because it's a constant, is just going to be 6. And you just need to equal them to each other. So my second function is actually so much easier. It's just b equals 6. Now I can plug in b into 4a plus b. I found my b value, which is 6. So I have 4a plus 6 equals 2. I'm going to send 6 to the other side as negative and divide each side by 4. So now I ended up with values a equals -1 and b equals 6 for the function to be continuous in the range of -3 to 0. So for this one, it gave us a piecewise function with an absolute value, and it wants us to evaluate the right and left side when it's approaching to 1, and then determine if it actually exists. So what I'm going to do, because it's an absolute value, we can actually separate it into 2 from left side and right side. So what I'm going to do is write the right side first. So I would take out from the absolute value as positive. So that would be x, took out of the absolute value as the positive version of it, because it's coming from the right side, x minus 1. And I'm going to put the condition here, if x is bigger than 1, which means it's coming from the right side. Now I'm going to put the left side in, so that would be x, put out of the absolute value as negative. So that would be I'm just going to put it like that, negative x minus 1 bracket over x minus 1, and that is only if x is less than 1, which means it's coming from the left side. So if we can actually see that I can cancel these x minus 1's from here. So the first version is going to be coming from the right side is only x. So that's if it's bigger than 1. And the second one I can actually see again, I can cancel these out, but I have a negative sign in front, so that would come up to negative x for anything less than 1. So from here, if I actually plug in 1 into these values, I would be ending up with 1 for the positive side and negative 1 for the negative side. So I can see that for the limits coming from the right side, so that represented by here, and limits for the left side represented by here, has different values. So one of them is 1, positive 1, one of them is negative 1. Therefore, I can say for these one-sided limits that they do not exist. So I'm just going to say does not exist. So I'm not gonna really draw the graph, but I'll just show just in case what it would look like. So the graph would look something like this. What I represented by green over here is another condition it gave us is when x equals to 1, it's 0. So we put that into the graph. And for coming from right side and the left side functions, they have to be unfilled dots. So this is representing 1 and the function x absolute within the absolute value, and this represents the negative portion of it.